All right, this is part 2 of section 4.9 dealing with antiderivatives. And in this video, we're going to talk about some of the indefinite intervals for trigonometric functions here. If you look on the left-hand side, you'll see the derivatives of some of the 6 derivatives of trigonometric functions. And then corresponding to those are their intervals, okay? So like for the derivative of sine of ax with respect to x, that's going to be the constant times cosine of a times x. If you recall, the derivative of the sine is the cosine. We copy the argument down, and then we take the derivative of that argument. So the derivative of a times x would be a. Now, if we go this way, take the integral of this, the integral of the cosine of ax dx would be this. It'll be 1 over a times the sine of ax plus c. Now, the second one is kind of tricky when you see it's in integration. For the derivative of the cosine of ax, the derivative of the cosine is going to be negative sine of ax, and then its inside derivative will be a, so it'll be negative a times sine of ax. Now, the integral of that is kind of tricky, and you have to think about this for a moment. The sine of ax, and you take its integral, it's going to be negative 1 over a times the cosine of ax plus c. And that's because if you take the derivative of the cosine, it will be negative sine of ax. And then you got the negative in front. So that means you'll have to have sine of ax dx. Okay. So here for the integral of the sine of ax dx, it's going to be negative. You don't want to leave that negative sign off. So it'll be negative 1 over a cosine of ax plus c. And then the derivative of the tangent of ax will be a times the secant square of that ax. Because the derivative of the tangent is the secant square. Now, if I had the secant square of a of ax dx, it would be 1 over a times the integral of the secant square would be the tangent. Because the derivative of the tangent is going to be secant square. So it'll be 1 over a times the tangent of ax plus c. And then the derivative of the cotangent of a times x would be negative a times the cosecant square of ax. But if we have the integral of the cosecant square of ax dx, we need the negative sign. And then 1 over a. The integral of the cosecant square would be the cotangent of ax plus c. So if you think about this, take the derivative of the cotangent, it would give you negative cosecant. Then this negative sign will make that positive. And then number 5, if you have the derivative of the secant of ax, that would be a times the secant of ax, tangent ax. Take the integral of secant ax tangent ax dx, that's going to be 1 over a times secant ax plus c. And a, by the way, is going to be a constant in front of the variable. And then finally, the derivative of the cosecant of ax would be equal to negative a cosecant ax cotangent ax. Its corresponding integral, if you just have cosecant ax cotangent ax dx, that would have to be negative 1 over a cosecant ax plus c. Because the derivative of the cosecant of ax will give you this. Then this negative will make it positive. All right, so do be familiar with these indefinite intervals for your trigonometric functions here, because we're going to use these to do some of these examples here, starting with example 9. Let's say we want to determine the indefinite interval, which is the integral of sine of 5y plus the cosine of 6y dy, and then check your answer by differentiation. So in this case here, I'll write this as the integral of sine of 5y plus the cosine of 6y dy. Then that's going to be equal to, let's use that sum rule for integration. I can write the integral of sine of 5y dy plus the integral of the cosine 6y dy. Now, if I take the integral of sine of 5y dy using this rule right here, sine of ax dx, that would be negative 1 over a cosine of ax plus c. I use that for that first piece. So that means that the sine of 5y dy will be negative. Now the constant in front of that y is 5, so it has to be negative 1 over that constant, negative 1/5. Integral of the sine will be the cosine of the 5y, and then plus cosine of 6y dy. Well, using this right here, there'll be 1 over a sine of ax plus c. So I'm going to have 1 over the constant, which is 6, times the sine of 6y. And then, of course, since it's an indefinite integral, I need to include that plus c. So all I'm doing there is applying those indefinite integrals of trigonometric functions to this example here. Now to do the check, I'll take the derivative of negative 1/5 cosine of 5y plus 1/6 sine 6y. And of course, I have to apply the chain rule on each one of these. And this is the derivative with respect to x. So the derivative of negative 1/5 cosine of 5y will be this, bringing negative 1/5 over. The derivative of the cosine is negative sine, so it'll be negative sine of 5y. Then I need the inside derivative. The derivative of 5y will just be 5 plus, bring over the 1/6. The derivative of the sine of 6y, or the derivative of the sine is the cosine, bring over the 6y, multiply that by your inside derivative. That's 6. The derivative of 6y is going to be 6. Now let's simplify this. These 5's divide out. Negative times a negative is a positive, so I'll be left with the sine of 5y plus these 6's divide out, you're left with the cosine of 6y. Which is exactly what I came up with, which is exactly the integrand that I started off with, sine of 5y plus cosine of 6y. So that tells me I have taken that integral correctly. Okay, so that's example 9. Okay, example 10. Say I want to find the indefinite integral. In this case here, the integral of 8 secant x tangent x plus 3 times secant square x dx. All right, so in this case here, I'm going to copy down the problem. The integral of 8 secant x tangent x plus 3 times secant square x dx. All right, so now I'm going to use the combination of the constant multiple rule and the sum rule for this. I'll have 8 on the outside times the integral of secant x tangent x dx plus 3 times the integral of secant square x dx. So I'm going to bring down to 8. Now, if I take the integral of the secant x times the tangent of x, let's go back here. Now, we're treating the a as 1 in this case here, so it'll be 1 over 1 or just 1 times the secant of x, okay? That would be your integral. So the integral of secant x tangent x would just be secant x plus, bring down to 3, the integral of secant square x. The integral of secant square x would be tangent of x, because the derivative of the tangent is the secant square. And then plus c. And guess what? That's as far as I can go with that problem. So its integral will be 8 times secant x plus 3 times tangent x plus c. And you can check by taking the derivative here. Bring down to 8. The derivative of secant x would be secant x tangent of x. Bring down to 3. The derivative of the tangent of x will be secant square of x. Okay. Let's look at this one, example 11. Determine the following indefinite integral. And we're going to check by differentiation. So here we got the integral of secant square 8x dx. Okay, so going back to this here, we can find the integral of the secant square of x. That's going to be tangent of x. And I'm going to be using that because I got that 8 in front of the x here. So its integral will be 1 over 8. The integral of the secant square would be tangent of 8x plus c. And we'll check by differentiation by taking the derivative with respect to x of 1/8 tangent 8x plus c. Bring over the 1/8. The derivative of the tangent of 8x will be secant square 8x. But of course, I need to take the inside derivative. The derivative of 8x will be 8. And then the derivative of any constant would be 0. So these 8's divide out. 1 times secant square of 8x would just simply be secant square 8x, which is the same as that integrand that I came up with to start. Okay, so that integral was taken correctly in that problem. Okay. All right. Be on the lookout for part 3 of this section 4.9 dealing with antiderivatives. Here I'm going to be talking about other indefinite integrals, and then I'll talk about differential, just an intro to differential equations. So be on the lookout for part 3 of this video.